An electric field varies with position and is determined by E xyz equals 2z x squared negative y newtons per coulomb. A negative 10 millicoulomb particle with a mass of 10 grams starts at r equals 132 meters. How far away from this point does it move, and what is its position after 1 second? We'll be revisiting iterations to solve this problem. It's standard problem solving for iterations to find our net force, and in this case, we're interested in the force of the electric field on the particle. To find the electric field at the particle's starting point, we plug in the components like so, and we get an electric field of 3 newtons per coulomb. Because we want the field to represent the system, we can use what we know about the electric force given by this equation and divide out the contribution of our object, the particle's charge, to obtain a representation of our system given by E equals F over Q. Now we can rearrange the equation to make it look like F equals Q times E to help us find the force of the field on the particle. Plugging in our knowns, the particle's charge is 0.01 coulombs and the electric field at the starting point gives us a net force of 0.04, 0.01, negative 0.03 newtons. Next in line is updating momentum with our momentum principle, and rewriting it, we have P final equals P initial plus F net delta T. Plug in an initial momentum of 0 because the particle isn't moving, our F net from the previous step, and a time step of half a second, and we get that our final momentum is 0.02, 0.005, negative 0.015 kilogram meters per second. Last thing for this iteration is updating position. Remember that average velocity is given by the change in position over change in time. Rewriting this equation, we get our position update equation, R final equals R initial plus V average delta T. Plug in the initial position, which is easy, then we approximate V average by dividing P future, which we just found, by the mass of the object in question, which is 10 grams or 0.01 kilograms. Finally, multiply the time step, 0.5 seconds. Let's make the second half of the equation nicer to work with, and we calculate our final position after half a second to be 2, 3.25, 1.25 meters. For the second iteration, we're basically repeating the updating of force, momentum, and position, but we have to be careful because the particle is now at a different position in space. So we plug in our new components to find a new electric field of 2.5 for negative 3.25. Update force as per usual by plugging in the particle's charge and the electric field to get a net force of 0.025, 0.04, negative 0.0325 newtons. Update momentum using the previous final momentum as our new initial and our new F net this time with the same time step so we can reach 1 second and get a final momentum of 0.0325, 0.025, negative 0.03125 kilogram meters per second. Finally, update position with the new R initial and P feature. Simplify the second half of the equation and get an R final of 3.625, 4.5, negative 0.3125 meters. Returning to the original question, we already know that its position after 1 second is 3.625, 4.5, negative 0.3125, and we use that to find how far the particle moved with this equation here, finding that it moved 2.625, 1.5, negative 2.3125 meters.